All right, welcome everybody to today's video. Today we're going to cover our introduction to assembly and really our first video covering content for the course. So we'll talk a little bit just about some introductory theory and some concepts, and then we'll move into the number system, base 10, base 2, and base 16, as they're very important to understand moving into the semester. Let's see. Right, so it kind of begins with how does a processor really work, and this is gets much more into the theory behind electrical engineering, which is beyond the scope of the course that we need to get into. There'll be some links throughout the presentation if you're interested in learning a little bit more about that. Definitely encourage you to follow that. However, I did want to spend just a few minutes talking about kind of how this works at a real basic level in order to understand the importance of the binary number and really to help us understand how assembly fits into the kind of the greater picture of the assembly language and how the CPU and those binary numbers and the operation codes, the opcodes that we're going to talk about actually work. So it begins with logic gates, and you should have hopefully studied those in your discrete math courses, and these operations. These logical operations are something that we'll talk about here throughout the semester. We start with basic input then, ones or zeros, because the base 2, the binary number system, is a 1 or a 0. And then we can perform logical operations on those, with the results of those logical operations then being used to further provide data or perform other operations. We have this component, there is this component that's called an adder. Adders are used in digital circuits to perform addition. Two types of adders, we have the half adder and the full adder. The difference between the two really boils down to the fact that the full adder will handle the carry signal, whereas the half adder does not. And we're only going to look at examples here for the full adder. Now, remember I said that these are for addition. And so what we have, and we'll look at binary addition. I mean, this is a little bit ahead if you've never looked at binary addition. But what we have then with the 1-bit adder is that we can take binary numbers as input, A and B here representing our input, and we can perform addition on them. So I can say 1 plus 0 in a base 2 system. The result of that is 1. S is our sum, and then we have a carry. And in this case, we had no carry, so we have a 0 on that carry. If we had a 1 and a 1, the result of that would be a 0, but then we would have a carry. We'd have a 1 set for that carry, because if we do binary addition on those two numbers, the result is a 1, 0. Right, so you can see these 1-bit adders then, 1 bit beings that they're taking two input sources, providing 1 out and 1 carry. If we were to chain these together, which we'll see in the next example here, 2 slides away, is that we can then, these full adders can handle the carry from a previous adder. And so, again, if you get deeper into kind of the electrical components, electronic components here, you'll see that we start to combine multiple adders in order to perform more complex operations. Truth tables, again, something that you probably should have, or hopefully you saw in your discrete math course. Truth tables give us all possible combinations of input to the mappings of the output. So it's all possible input combinations with all possible output combinations. And with these two particular truth tables then, you can see that this one here is for our half, and this one here is for our full adders, that is. And we know that because, excuse me, and we know that because we have, for this particular truth table, I said that the half doesn't support the carry in. So we just have two inputs, A and B, but for the full adder we have A, B, and then our carry input signal. Right? So the truth table then goes through every possible combination of input. If we just have two inputs, A and B, we have 0, 0, 1, 0, 0, 1, 1, 1, and these are all the possible combinations of output. Same with the full adder truth table then, all three possible combinations of input and all possible combinations of output, the carry signal as well as the sum. Right, so from addition, you can implement other operations, multiplication, division, shifting, all of these that we'll talk about at the assembly level here throughout the course. And so what we end up having then is a variety of operations acting on one or more inputs. Because we want to use them to perform these operations, we need to be able to temporarily store that data while the CPU is performing that instruction. And so we have a series of registers, which again we'll talk about more as we get into the course, and that we can perform these operations. We can take these inputs, we can move things around into registers, perform operations, store results into registers, and then continue to execute a program. The operations are encoded in a bit pattern. And so you can see with these examples here, these are just hypothetical. These aren't actually or necessarily the actual operation code in binary. Just as an example though, as we can say that this 4-bit number, each number representing a bit, so these 4-bit numbers, this will perform a NOT, and this will perform a logical AND, and this will perform addition. And so that's how we take and store the instructions for a program, for the CPU to execute in a binary number in a system, and that system is able to interpret what that instruction is. We want to add data to it. So let's say that we want to add 6 and 2. And so we can send the instruction for adding. We covered in the last slide that that instruction might be something like 0, 1, 0, 0. We encode or change, I shouldn't say encode, we change that by that number 6 and 2. I'm representing this as a base 10 number right now. And we convert that into binary. And now we have this instruction, 0, 1, 0, 0, and 0, 1, 1, 0, 0, 0, 1, 0. So we can say, or tell the CPU to add 6 and 2. Right? So now we can have a sequence of operations. And that's really what's fed into the CPU, is all of these binary numbers, all these instructions that the CPU is just constantly executing. This is difficult because this would be very difficult to program, to create programs if we had to actually write this in this binary format. And so what we have is we have programming languages that have come along and made our lives a lot easier. Assembly is kind of the second highest level language from the actual opcodes, from this actual binary level. And so assembly compiles into the machine language, and assembly provides us with a bunch of mnemonics that map to that machine code. And so instead of having to write something like this in binary, what we can do is we have mnemonics. This would be a mnemonic here, these would be mnemonics here, to say add this number, add 6 and 2, add this value to this register. And so now things become a little bit easier because we have these shortcuts really that help us in determining or writing our program. And so we'll deal with and work with a lot of these mnemonics here throughout the course. Right, again, how does a processor work? We have a series of gates and different types of or different implementations. I don't want to go too deep into it, but I did want to leave, I toyed with taking the slide out. I did want to leave this in here just in case you're interested and you have the time to go and dig a little bit deeper into the electronic theory behind how processors work. It's very interesting, but it's definitely not necessary to get through the course. So just wanted to leave this link and some topics here for you to further research if you have the time and the interest. Right, talked about the adder, a slightly different representation of that. This is more of a logic diagram, and again, you may have seen these in your discrete math course. A and B are operands, A and B are inputs, as well as the carry, and then we have the sum, and we have the carry out. And so we could take a look at, again, doing an example here, and just like we did previously, where we have our input 1 and 1, and let's say that our carry in is 0. 1 plus 1, that sum would be 0, and our carry would be 1. And so now that is the basic logic that is implemented using these digital components, these electronic components, down there at that lowest level, the actual build the CPU. We can take the adders and we can combine then multiple adders to add multiple numbers. And so let's say, for example, that we wanted to add the number 1 and 1 and another number 1 and 1. Well, we have the addition that's performed with this single 1-bit adder. So we have the result of that. So the sum is 0, but we have a carry. And we do the same thing here. 1 and 1 is 0, and now we add the additional carry bit. So now we have the result being 1, and we have another carry. So we could stop there, and we could see, in this particular case, that the final result would be 1, 1, 0, 0. Now, at this point, I do also want to point out that you have a calculator, whether you're in OS X or on Linux or in Windows, you do have your calculator available to help you with some of these conversions. Each view of your calculator is probably going to look a little bit different than what I have here. You can change that probably to your programmer mode. That's going to be the most conducive. And the one on Windows, at least Windows 7 as well as OS 10, has this binary display here, which is very handy at this point in time because it allows you to look at binary numbers. And so we could take this binary number and we could simply flip these bits here in our calculator, and we could see that, because I'm selected base 10 mode, that binary number is 6 in base 10. We could kind of figure out, make sure that our addition was correct here, and we could say that 1 and 1, so what is that in binary? 1 and 1 is 3, so 1 and 1, so 3 plus 3 is 6, and that helps as well. So you'll see me use my calculator here throughout the course just as a way to verify what we're doing, to make sure that what we're doing is correct, to make sure that the process we just went through and the number or the result that we came up with does in fact make sense. So please use your calculator accordingly to help you with that. Right, so how do we write programs? And we'll be getting into the next lecture actually writing assembly. We still have a little bit more here background information to go through. But we have, as I mentioned, a series of opcodes. And those opcodes tell the CPU what to do, as well as one or more operands or data that can come along with that operation, or that opcode, that instruction, addition, subtraction, multiplication, moving data around. All of these operations we're going to use extensively throughout the course in order to write our programs. With each clock, we increment with each clock cycle, so our CPUs run in gigahertz, and with each one of those cycles, we can increment the program counter. And what that is doing then is it's loading the next instruction. We figure out the opcode and the data, and then we repeat. And so the process of loading in that next instruction, figuring out what that operation code and what data is associated with it, if any, and we just continue to do that. So that's the loop essentially that our processor is in, never ending until we power it down. So as I mentioned, assembly is the lowest level language. We have written the assembly language itself then is written for a specific architecture. And so you have things like i386, the ARM, a SPARC cell processor, which was in the PS3. Not sure what the PS4 is in. In each assembly language, all the mnemonics then map to the specific instruction set for this whatever particular architecture that you're on. And so we'll be looking at the 32-bit Intel operation code instruction set throughout this course. And we'll probably dabble there at the very end a little bit into the actual 64-bit stuff, but because 64-bit doesn't really change a whole lot from 32 to 64-bit, other than the size of the registers and some of the other things that we'll work with, it's just as easy to start with 32-bit. All right, so assembler translates to binary native code, and we'll also be using a compiler to link our code. And we'll talk a little bit more about that here as we get move throughout the semester. There are different assemblers out there. This becomes more important as you move beyond 314, as you move beyond our intro to assembly programming, particularly the reverse engineering course, because when you go into, for that course in particular, when you start reversing or reverse engineering a binary, it's important to understand how it was built and what type of an assembler was used to generate that code. MASM is the Microsoft Macro Assembler, and I'll be using that one more in CSC 444 if you take the course. There's the Turbo Assembler, there's NASM, which is the Net-Wide Assembler, and this is the one that we'll be using for this course. There's a GNU, GNU's the GNU Assembler, or GAS. So a handful of them out there, and the differences can be in how those assemblers, how they generate that native code. So why do we program in assembly? Well, there's probably two main reasons that I can think of here. One is to really understand the lowest level architecture, and it's kind of a side story. I took assembly as an undergrad several years ago, and I didn't do all that well, and I really didn't see the relevance of it to the kind of programming that I wanted to do in my career. It wasn't until I came back to academia and started teaching assembly and did it. I guess it really finally clicked. So sometimes it can take a while for things to get through my head, but it really clicked, and I saw that there's a tremendous amount of value in understanding assembly, and understanding how the CPU works, understanding these opcodes and how our programs, what they get compiled into. It helps to write faster, more efficient code because you understand how those instructions are being executed at the CPU. If you go into lower level programming, you do device drivers or embedded systems or real-time systems, you might end up doing or programming in assembly or a very low level or I guess a language like C. The other option, or maybe the other important, is the reverse engineering course, and preparing, specifically because you're taking this at DSU and you might be in one of the programs that then requires you to take reverse engineering. This does become a foundational course in getting through the reverse engineering course. You can also look at shellcode, and we'll take a look at that later in the semester. What is shellcode, and how can you generate your own shellcode so that you're not dependent on somebody else's shellcode? You use shellcode a lot with things like Metasploit and trying to gain access or exploit a system. And if you don't understand how that shellcode, how to look at that shellcode in a way that you understand what it's doing, you're leaving yourself maybe a little bit open there. All right, so we have some architectures, in that we have these different layers of languages. And this is really all I wanted to point out here. Is that level 1 is the digital binary logic, level 2 is the instruction set defined by the processor makers. So like we were talking about just a couple slides ago, Intel, SPARC, ARM, each one of these is going to have its different ISA, instruction set architecture. And so you'll have to know if you're looking at, you'll have to be aware of what architecture that your code is compiling down to. Level 3, this is where we'll spend most of our time here with the assembly language. And then level 4, we have our high-level languages like C, Java, Perl, etc., which is where most programmers spend their time, at this level there. Right, so computers only store bits, ones and zeros, and all of that really was kind of a lead up to start talking about the different number systems that we can use, base 2, base 10, base 16. And so when we program an assembly, we not only need to understand those, and we need to understand how to move back and forth between those different number systems, the binary, the hexadecimal, the base 10 being the one that we typically write in or use on a daily basis. We also have to talk about something called 2's complement, which is a way in which, if all we can store are ones and zeros in a computer, then how do we store negative numbers? How do we represent a negative number? Well, 2's complement is a system in which allows us to store a value, a negative value. So we'll start off with base 2, which is our binary number system. Just read that here. Okay, so each bit is 2 to the n in decimal. And what does that mean? Well, that means something like this is probably going to be the easiest way, especially if you haven't spent much time with binary numbers, and figuring out how to write a binary number. Either how to write the binary number or how to convert a binary number into decimal, into base 10. And so we have 2 to the n. So the total number of digits that we're dealing with, binary, we only have a 1 or a 0, so we have 2 to the power. And that's the number of places in this table that it would be. So we start off with 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3, and so forth. That sequence goes on incrementally. Each time the power is added, we add 1 to the previous power, and that is our result. So 2 to the 1, 2 to the 0 is 1, 2 to the 1 is 2, 2 to the 2 is 4, 8, 16, 32, 64, 128, and we just would keep going, 256, 512, 1024. And so if we want to, for the first example, figure out what is this number in binary, what is that in base 10, well, you can write down a truth table like this, and then put in whether or not, or fill in that binary number below it. If there's a 1 bit, then we have that value. So we have a 1, so we have 2, we have 32, and then we have 64. Okay. Once we do that, we just add the numbers together. So this would give us 64 plus 32 is 96 plus 2 equals 98. Right? And because we have our calculator handy, we can always go back through and verify. So we have 0110, 0010, 98. And so right there is our binary number. That's the result that I said, and that's how we figured out that answer. Right? So we have the truth table. We fill in below that the binary number, we look at where the bit is set, where there's a 1, and we get that corresponding value. Once we get that, we sum them up, and that's our answer in base 10. And I guess I have the answer right there as well. To go from decimal to binary, then we can do this in reverse, and there's a couple of ways we'll do this. The first way, probably the easiest, or not, I shouldn't say easiest, but easier way. Let's change colors here real quick. Is simply to take a table like we have here, figure out, let's say that we want to do the number 64. Right? So we just write down our table, we go through, and we find what is the biggest number that is not greater than the number that we want to convert. So this one's easy, 64, so we'd say that's our number. That is our number, so we'd have a 1, and then the rest of these become zeros. And that would be our result. If we wanted to do something a little bit more challenging, let's say that we wanted to do 102, well, we'd follow a similar process. 128, that's too large, so the first biggest number that doesn't go over, that's not greater than the number that we're looking to convert, is still 64. So we take 64, we have a 0, we set a 1. 64 plus 32, that's 96, that's still less than, so we take that one. 16 plus 96, that would take us over, so we set a 0. Let's see. 96 plus 8, still too much. 96 plus 4, okay, so that would give us 100, and then 2 would give us 102, and now we have our 0. So that would be how we'd write that number. What you're going to find, though, is that we typically work in 1 byte, or 8 bits. 8 bits equals 1 byte. And so what you're typically going to see is that when we write a binary number, we write all at a minimum where we're going to write in bytes. And so we're going to write at a minimum 8 bits, regardless of what that number is. And so here you can see that even though I don't need this leading 0, because we didn't use that, we still set that 0 to make sure that these are both 4-bit groupings to be 8 bits total, so that would be 1 byte represented in memory. And again, we'll deal with that more and more throughout the semester. So, all right, another method is the division method. And this is probably a lot more time-consuming, but something that's worth going over. Let's say that we start with another relatively easy number, and I'm going to pick a better color than red. So we start with 64 again. Okay, what we do is we take that number and we divide by 2, and we get the remainder. So we'll say that the remainder here is 0, because 2 will evenly divide into 64. We divide that by 2, because that's the result. Divide that by 2 again, and we have 0. So we just continuously divide the number that we want to convert by 2, and we essentially record what the remainder is. Right? 16 divided by 2, 0. 8 divided by 2, oops, 0. Okay, we're almost there. 2 divided by 2 is 0. And then finally we get to 1. 1 divided by 2 is 1. Right? And that's the result then. And so how we would write this binary number, or write this result using this division method into a binary number, is we'd start with the last. That would become the first or the most significant bit. So we say 1, and then we have 1, 2, 3, 4, 5, 6. So a 1 and 6 zeros. And there's our binary number. And if we wanted to make sure that that was 8 bits, we could write that leading 0. Right? And then we can make sure that our math is right. And we could say that this is 1, 2, 4, 8, 32. Oh, looks like I'm off somewhere. Oops. Oh, I see what I did. Okay. I skipped a number, so I was right. I just made a mistake here in what I was writing down. So 16, 32, 64, and then 128. There we go. So I was right, and that's our number. So the division method it was successful in converting 64 into a binary number. All right, so divide by 2, get the remainder. Divide by 2, get the remainder all the way until there's nothing left. All right, binary addition, we've already seen this a little bit, talked about this a little bit, becomes, I guess in a way, relatively straightforward in that we take a number, so let's start with two numbers, 1 and 0, and if we want to add those together, the result would be 1. 1 and 1, add those together, we'd have a 0 and a 1. That would be the result in adding those in binary. 1 and 0 would be 1. And of course, 0 and 0 would be a 0. Right? It gets a little more complex when we start to add multiple numbers. So we could take something like 1, 0, 1, and we could add those together. And we get 1 and 0, which is 1, plus 1, which is 0 with a 1. Right? Or 1, 1, and 1. Okay, 1 and 1 will have a carry. So we have a 0 here, but then we add 1 to it. So we have a 1, and then we handle a carry. So we have a 1 and a 1. Right? And we just keep doing that, no matter how many numbers, how many bits we're adding together. We can take more complex numbers, and that we have more bits that we're adding to it. We can say 1, 0, 1, 0, plus 0, 1, 0, 1. Add those together. The result of that would be 1, 1, 1, 1. Do something like that. 0, 0 with a carry, 0 with a carry, and then finally 0 with a carry. Right, and then, so that's the process that we follow. Once you get this the basic process of adding down, the rest of it becomes relatively straightforward. And you're just applying what happens here. When do we have a carry? When we don't have a carry, over and over again. So relatively straightforward there. Okay, so that's base 2. I'll assume that you're comfortable with base 10. The other number system that we're going to deal with a lot, and we'll deal with this quite frequently with assembly programming here with the course, is hexadecimal, which is base 16. And what this allows us to do is it allows us to represent numbers using the characters 0 through 9 and A through F. And so we expand our character set. Binary has 2, 0, 1. Base 10 has 10, 0 through 9. And hexadecimal has 16, 0 through F. And so what happens then when we get to 10, if we're thinking in that base 10 format, when we get to 10, we go to A. So A represents 10 in base 10, B is 11, C is 12, and so forth. So we have 16 values, but it's 0 based, remember? So from 0 to 15. And what you're going to find that this is, not only is it more compact than binary, it's actually relatively convenient to use because we have 1 byte is equal to 2 hex digits. And what I mean by that is that if we have, and you're going to see this in the next table here, is that if we have a hex digit, what I mean by a hex digit is 4 bits. So let's say that we take 4 bits here, and we write that in hex, Well, we can figure what this is in base 10. So we'd say 1 plus 2 plus 4 plus 8, which would be 15. 15 is our last hex digit, so F. So if we convert this to base 16, that would be F, right? So one hex digit equals 4 bits. With 4 bits, we can represent the values from 0 to 15, right? This is the maximum. The maximum 4-bit number will have all ones, and that's a value of 15 base 10, which is a value of F. And so 2 hex digits, we talked about 1 byte being 8 bits. 1 byte then can be represented using 2 hex digits. So that would be 10, that would be A. Right, so that's what that statement is telling us. Again, very important to understand this, and so we'll have some practice here in a little bit on the second quiz. Actually, the first quiz is just an introduction. The second quiz, and then throughout all of the course. Multi-bytes, you can use a base 16 multiplier, right? So just like we had with the base 2, where we had 2 to the 1, 2 to the 2, 2 to the 3. You can do the same thing using 10 by 16 to the 2, 0 by 16 to the 1. You know, you're just changing this value here and the power that it goes to based off of the position that it's in. So you can follow a very similar format. Use your calculator if you need to. Right? It's important to be able to do this relatively quickly in your head, but definitely getting started, use a tool like this in order to help you get started. Right, here's a chart that shows us really the conversion and all values in a hex digit. A hex digit then being our 1 hex character or a value in base 10 of 0 through 15. Don't worry about the octal because we're really not going to cover octal throughout this course here. Not all that important at this point in time. And so we have our hex digit, we have our decimal, and then we have what is that value in binary. So you can see here, of course, it's 0, 0. We start with all zeros. An A in hex is a 10 in decimal, and just like we saw on the previous slide, it's 1010 binary. Little cutoff here. This looks better in the actual PowerPoint, and I'll provide both formats to you, this one that I'm marking up as well as the original PowerPoint presentation. F, the last hex value that we can have, which is 15, 15 in base 10, and all bits are set. So we have a value of 1111. Notice kind of the pattern here, that as you add, as we go from 0 to 1 to 2 to 3, we're just simply adding another value. So from 0 we add 1. From 1 we add 1, which becomes 10. We add 1, 1, 1. We add another 1. That becomes 1, 0, 0. Right? We'll go through a few of these here in the next slide. I'm not going to go through all of them just for the sake of time because this table here outlines how the hex digit, 1 hex character, 1 hex value, maps into 4 bits. Right? That's really the important takeaway from this one. All right, so we could recreate that, and I'll just do the first few values here just to show you that pattern. So let's say that we start off with 0 in binary. That would be 0, 0, 0, 0. And then 1, we just add 1. So we have 0, 0, 0, 1. We go to 2, we add 1. So what's binary addition 1 and 1? Well, we have 0, 0, 1, 0. Okay. 3, we add 1, 0, 0, 1, 1. 4, we add 1, right? And now we'll have carries. So if we add 1 to here, we'll have a carry. So that'll be 0 with a carry. 1 and 1 is 0 with a carry. And then 1 and 0. Right? And now that process just repeats. You just keep adding 1 until you get to a value of 15, or all ones in that binary number, or F in hexadecimal. Right, so the next challenge then is in converting between binary and hex and base 10 and all of the between, all possible combinations thereof. And so this is what the second quiz, the quiz that you'll take next week, will allow you to practice, because again, it's very foundational. It's very important that you're comfortable in identifying how we go through back and forth between binary numbers and hexadecimal numbers and what they mean. And so we go through the conversion process. Ways that I like to do it, this makes it easier for me, and if you come up with a better way, great. I'd love to hear about it. Ultimately, it's up to you, what makes the most sense for you. What I like to do though, because we typically work with bytes, and we typically then have within a byte, you have four bits will equal one hex digit. I kind of look at those as four different values here, or two separate groupings, as you could say. And so once you do that, then all you have to figure out is what is this value? Because the goal right now is to convert these into hexadecimal, right? So we have 4 bits. Right? 4 bits is the maximum bits that we can use to represent a hexadecimal character. So we have 1, 2, 4, 8. So in hex, this would be 8. Right? 1, 2, 4, 8. So 8 and 4 is 12, plus 2 is 14. 14 is 1 less than the maximum, which is F, so we know that's E. Right, so there's our hexadecimal number. You'll probably see that hexadecimal numbers, I'm going to represent them myself quite frequently with a 0x in front of those, and that'll become a little bit clearer here down the road. But again, we can verify that. So if we go back to our calculator and I say 1, 1, 0, 1, 1, 1, 0, 1, 0, 0, make sure that your calculator is in base 16. You can see that that gives us a result of E8, which is what we came up with. Right, and now we can just repeat this process. So I can say that this value here, 1010, that's 10, base 10. So that's A in hexadecimal. And 1 is just simply 1. So we have A1. Okay, now going from hex to binary can be, it's not really, we really just follow the same process, we just do it in a reverse order. Each one of these hex digits represents 4 bits. And so all we have to do then is write out what, switch colors here. A little bit darker blue. All we have to do then is convert that each individual hex digit into binary and then just write that out as one contiguous sequence. So A in binary is 1, 0, 1, 0. Okay, F is 1, 1, 1, 1. 0 is 0, 0, 0, 0. And 2 is 0, 0, 1, 0. Right? So that's our result. That's our binary number. And we can use the calculator to help us confirm that. AF02. And we can see, so we have 16 bits, 1010, 1111, 00000010, which is the result that we came up with. So we can see that those match up. Again, same process here. Right? So what's F? All 1s. And then the last 8 bits are exactly the same as that last example. All right, so the only other thing that we haven't gone over yet then is how do we convert from base 10? And so let's say that we have 102 and base 10. How do we go back and forth between that? Well, again, it's really up to you if you find a way that is the most convenient for you to do that. What I typically end up doing is converting this number into binary first, and then from binary I convert it into hex. And I laid this out here in the slide to kind of show you that process. And so if we look at what would this be? What numbers do we need? Well, we could start by essentially writing down that table that we first started off with when we talked about binary. So we could say 1, what are our values? 1, 2, 4, 8, 16, 32, 64, and that's as high as we'll need because 128 is greater. Right? So we know that we'll need 64, we'll know that we'll need a 32, that gives us 96. We won't use a 16, we won't use the 8, 1, and 2, and then 0. So there's our binary number written out in 8 bits. So now I can just move this over here, 0, 1, 1, 0, 0, 1, 1, 0. Now we can convert each 4 bits into its hex equivalent. So 1, 2, 4, so that's 6, and then that would be 6. So the hexadecimal value would be 0x66. And as we previously have done, we can always check that. So it doesn't hurt just to take a look, 66, 0110, 0110. So we know that we've gotten that conversion right. And if now we want to flip this from base 16 to base 10, that'll convert that number for us. We can see that it's 102, which is the original number that we started off with. Right? So we can see that our math went correct. The conversion process was done correctly from base 10 into binary and binary into hex. Okay, last thing that we need to tackle today is the 2's complement. And there is a so when we deal with storing numbers, we have 1s and 0s, and there's no inherent way to represent a negative number inside of that system. And so what has been developed is something called 2's complement. And what 2's complement does is we signify the signage of a number based off of the most significant bit. Let me see if I can change my... And so let's say that we have a simple byte, an 8-bit number, and we'll just set these all to 1s. And what we have then is this becomes the most significant bit, and this becomes the least significant bit. Right? Most significant. That is that this bit here has the highest value, will have the largest impact on the overall number. It also is the leftmost bit. Right? So most significant, least significant. What we do with 2's complement then is in a 2's complement system, the most significant bit is used to determine the signage of the number. And so a 1 means that it's negative, a 0 means that it's positive, and these other bits then are used to determine what is the value of that number. And so when we store a number in 2's complement, we don't have all 8 bits to represent the number. We only have these 7 bits right here. So in 2's complement, we lose the total max value of a number because we lose that bit, the most significant bit, in order to determine the signage. That's something to consider when you're programming and you're looking at the different types that you can choose, unsigned versus signed. Unsigned can store a larger positive value because we get that extra bit back. A signed number, then we lose that. We have a negative value that we can assign, but our maximum value is less because we lose that bit. How we then determine, there's a process, there's an algorithm when the most significant bit is set. What happens is that we have to go through a process when the most significant bit is set. That process is this simple algorithm right here. We reverse the bits and then we add 1. So probably the easiest way to look at that is to look at an example. Right? So let's say that I tell you that this number, this binary number, is stored in 2's complement. First thing that you want to do is look at it and determine that the most significant bit. This is our most significant bit right here. Most significant, this is the least. Right? Same with this number right here. Most significant and our least significant. So we see that this is the most significant bit is set in this case. So we have to apply that process, that algorithm. We reverse the bits, we flip the bits, and then we finally add 1. So if we flip all the bits, we come back to this number, and we just simply flip them. 0, 0, 1, 0, 1, 1, 0, 1, and then the last step is to add 1. So we have 0, 1, oops, 1, 1, 0, 1, 1. It's hard to read there. All right, and that's our value. So now we have a binary number. If we wanted to determine what the value is in whether it's base 10 or base 16, we would simply do that conversion. And so, let's see, we have 2, 4, 8, 16, 32, and 64. So we add those numbers up. We get, what do we get? I think we got 110 or something. 96, 110, right? So that result in base 10 is 110. This represented a negative number, though, right? We just went through this process because we determined that the most significant bit was set, and so then we finally have to make this a negative. Right? What happens if I say this number here is stored in 2's complement? We go through the same process. The only thing that changes is the fact that we look at the most significant bit. It's not set. Since it's not set, the only thing that we do is figure out what this is, what the value of this number is. We don't have to we don't flip the bits, we don't add 1. So that's a 2, 4, 8, 16. The result of this would be 18, and that's our value. Right? This one bit being flipped changes the value drastically. If it's a negative, if the most significant bit is set, we flip the bits, which is what we did here. We add 1, and then we can convert that into whatever number, knowing that it's negative. If the most significant bit is not set, then we don't do any bit flipping. We don't have to add 1. We simply figure out what the value is based off of changing the binary number into base 10 or base 16. Right? So that one bit has a pretty significant impact on what the ultimate value is from that number that's being stored. All right, the last process that we'll go through then is how do we store values in 2's complement. So let's say that I give you -8, and that's in base 10. So I'll make a little note here. All right, so how would we do that? How would we write that? Well, we would just do really the same process in that we would write the number in binary. So we would say, let's see, 0, 0, 0, 1, 0, 0, 0. Okay. Now we flip the bits. And now we add 1. So it's the same algorithm to get the result, which this then becomes, right? And so there is our binary representation in 2's complement of the base 10 value -8. And so then we can check this. This is what we said our result is. We can check it. We look at the most significant bit. We see that that most significant bit is set. So we know that it's going to be a negative number. So we just do the exact opposite. We flip all the bits. So we have 0, 0, 0, 0, 0, 1, 1, 1. We add 1 to it. And that gives us, those first 4 bits will stay zeros. 1, 0, 0, 0. 1, 2, 4, 8. So we know that in base 10 that is 8, and it was a negative value, so we add a negative sign to it. Right? And so that's how we go through the conversion process from base 10 to 2's complement, storing it in as binary number. All right, so again, quizzes will be over. You'll have time to practice these, but of course, if you have any trouble with anything, please let me know. Same with the writing here. I'm using a little tablet thing here to help write these on here. I'm trying to go a little bit slower just to make sure that everything's legible, but if there's any trouble with anything here, if you're not able to read these or see these or understand these, let me know so that I can either try to do a better job with writing them, which I'm not sure I can, or finding a different way in which to do this. Beyond these first couple lectures, I won't end up doing a lot with this writing, because we'll start looking at assembly and writing assembly, and we'll do a lot of things just based code. All right, so as far as the number system then, so storing things in binary, we have character sets, and there's a variety of character sets that we can look at. Typically, we deal with ASCII character set here in kind of the Western world. With an ASCII character set, then what we have is we have 8 bits for a single character, so 2 hex digits. For letters and numbers, the most significant bit is 0, and in assembly we can convert from a char to a byte, and you'll see that with C as well. You can go to ASCIIcode.com, ASCII-code.com, which is this right here, and this allows us then to look up any character that we want and figure out what is this value in decimal, octal, hex, or binary. And so if we went through this particular table, let's say that we wanted to look at the ampersand, we could see that it has a decimal value of 38, base 10, a hexadecimal decimal value of 26, or a binary value of 00100110. And so these character sets, again, this is how we're storing, how the computer stores information in a binary form, and yet can convert it into something like a character that we can see and we can interact with and make sense to us as a human being. There are other character sets out there, UTF-16, Unicode, UTF-32, and what these did then, you can see here with the number, is that they expanded the number of bits available to store those characters. Instead of having only 8 bits, you can have 16 bits and 32 bits. Where we run into those issues is really kind of the non-Western languages, the Chinese or some of the Asian character sets that are far greater than the possible number of combinations that we can store using an 8-bit character. And so some of those will use those, some programs will use wider character sets. Some programmers will choose to use those for a variety of reasons. A lot of times you'll notice that when the program is trying to support an international character set, so something that's not just what we typically look down on our keyboard and see. All right, that's it. This is a little bit lengthy of a lecture, and all future ones will be much shorter. So thanks for hanging in there with me. If you have any questions, this stuff is very foundational for the course. So if something's doesn't make sense, if I didn't convey to you how to do something, please let me know so that we can get you squared away and moving on the right path. So let me know if you have any questions, any issues. Otherwise, I will see you guys in the next video, and we'll go from there. Thanks.